There are different ways that we can use to determine enthalpy change or change in enthalpy for a chemical reaction. So I'm going over a specific example where we're using chemical energy to determine the enthalpy change for a chemical reaction. And remember, chemical energy is that potential energy that is stored in chemical bonds. So you have a table there and it's listing different chemical bonds and an amount of enthalpy. That amount of enthalpy that you have for those specific chemical bonds is the bond dissociation energy. It's telling you the amount of energy that is required to break apart those specific chemical bonds. So when you're breaking apart chemical bonds, energy is required. It's an endothermic process. So for example, if we look at the bond between carbon and hydrogen, the second one listed on the table, CH, to break apart that carbon and hydrogen, right? Carbon, hydrogen, that's forming a covalent bond, sharing electrons. So if you want to break apart that carbon and that hydrogen, it is required an input of 415 kilojoules of energy per mole of CH. So that's telling you how much energy you need to break that specific chemical bond apart. So when we're thinking about breaking chemical bonds, what we're thinking about is endothermic process. It requires energy. When you put together your electrons to form back a chemical bond or to form a chemical bond, that is an exothermic process. It will release energy. Now, the bond dissociation energy is given as a positive number. It represents like breaking chemical bonds. But when the bond between carbon and hydrogen is forming, that formation is going to release 415 kilojoules of energy. Now, when we're looking at a chemical reaction, you have your reactants and your products. The initial, it's your reactants, right? That's what you're starting the reaction with. So you have in your reactant, every single chemical bond on your reactants has an amount of energy or a chemical energy associated to them. So for your reaction to actually happen, all of those chemical bonds, they have to be broken. And then your atoms are going to be rearranging to give you your new substances, the ones that you're getting from that chemical reaction, which are your products. So you have initial amount of energy in all of those chemical bonds. And now, right, you have amount of energy on the chemical bonds on your product side. So we can calculate an overall amount of energy or that enthalpy based on the difference between how much energy you have in the chemical bonds on the reactant side, how much energy you have on the chemical bonds on the product side. So I have an equation right there at the bottom of the page which allows us to calculate enthalpy change for a chemical reaction based on the numerical value that we have for that bond dissociation energy. So the bond dissociation energy is something that we can find very easily. There are tables with a lot of different values for different chemical bonds. So in the equation what we have, it's an enthalpy change that is determined at standard conditions or under standard conditions. So the difference between this symbol here, you see how I have delta H and a small degree sign right there. That degree sign means that we're using standard conditions or values determined under standard conditions. So what are the standard conditions that I'm talking about? So standard conditions are measurements like the pressure, it's at 1 atmosphere. The temperature is 298.15 kelvins. If you're using solutions, the concentration for the solutions will be 1 molar. So when we're looking at the table for the bond dissociation energy, those values in the table are determined under standard conditions. So there's no difference in your numerical value based on temperature, pressure, or concentration. The difference between the numerical values is actually coming because your different chemical bonds will have an amount of energy that is different associated to them. So there's no effect of the temperature, the pressure, or concentration on those numbers because all of them are determined under the same conditions. So since we're using all of those numerical values that are determined under standard conditions, the enthalpy change that we're calculating, it's also standard conditions. So we have that symbol, degree symbol, added to that delta H symbol. So let's do one problem so we can go over the equation. On the equation, you have the symbol for the sum, which is this symbol right here. That's the sum of the delta H for your bonds that are being broken. So the first term right there is for the reactants. The bonds that are being broken are on the reactant side. So every single bond that is being broken, we need to add that amount of energy together for all of the sum of. Now the second term in your equation also it's a sum of. But now what we're adding is the delta H, or the numerical value that we have for the bond dissociation energy for all of the chemical bonds that are being formed on the product side, because on the product side is where the chemical bonds are actually being formed. So this one here, it's for the products. The enthalpy change for the given equation that you have right there. So we have a list of bond dissociation energy given for different chemical bonds, which are the ones that we have in that chemical equation. So we're going to be using the equation that we have, that we went over previously, to calculate the enthalpy change for this reaction here. So I'm going to rewrite the equation, like to write down the equation that we need first for the reaction Rxn, and this will be the sum of so we have the sum of the bonds that are broken, that are being broken on the reactant side, minus the sum of that enthalpy change for the bonds that are being formed on the product side. So that's the equation that we're using to find out that enthalpy change. And that enthalpy change will be a standard enthalpy change because we're using standard values given in that table right there. So I'm going to do something else with my equation before I move to the next step. So in my equation here, I'm going to add my coefficient, even if it's a 1, okay? And you will see why. So I have 1 mole of CH4 plus 2 moles of O2, forming 1 mole of carbon dioxide plus 2 moles of water. So I'm going to write down my equation now, just showing all of the chemical bonds. Let me leave space here. H, this is CH4, and then I have this coefficient for CH4 is just 1. Then I have 2 coefficient for O2, and O2 looks like this. And then I have a coefficient of 1 for CO2, and CO2 looks like that. And then I have a coefficient of 2 for water, and that looks like this. Okay, so let's start counting the chemical bonds that we have. I'm going to put in blue CH4. Every CH4 has an amount of energy equal to 415. So CH4, carbon, hydrogen, look, I have 1 carbon hydrogen bond there. That's 2, 3, and 4. This is 4 carbon hydrogen bonds, and each one has an energy equals to 415. 415 kilojoules per mole. Now for CH4, what we have is my coefficient right there, which is 1 mole. So you get to see how the units are canceling out. And whatever amount you're calculating for that, it's in kilojoules. We have to do the same thing with everything on the reactant side. So now for the next one, you have 2 moles. So I'm going to write down 2 moles. And now for the oxygen, look, oxygen, double bond between oxygen has an energy equal to 498. So you have 2, and that will be times 498, because there's just 1 double bond, right? It's just 1 right here, times 2 moles. That will give you 2 times 498. And then this 498 has units of kilojoules per mole. Mole cancel out, and you get a number in kilojoules. So this is what the sum of means. You're adding together all of the energies on your reactant side. So all of this is for the reactants. So that will give you a numerical value, how much energy it's coming from breaking, or how much energy it's being used breaking apart the chemical bonds on your reactants. And now let's check what we have on the product side. On the product side, we have C double bond oxygen. So this one right here is this one right here, and each C double bond oxygen has an energy equal to 799. How many we have of them? Look, C double bond oxygen, C double bond oxygen, that's 2 of them. In each carbon dioxide molecule, you have 2 double bonds between carbon and oxygen. So it's similar to the CH4. The 4 is coming from the 4 bonds that you have in the same molecule. Okay? So the 2 is coming from the 2 double bonds that you have in the same molecule. This is 1 mole from the coefficient. And each carbon double bond oxygen is 799 kilojoules per mole. And we're missing the last one, which is HO2. So hydrogen, oxygen, let me see which color I have not used. HO, 464. So let me start by writing down my coefficient here. That's 2 moles. And then in the same water molecule, I have two oxygen hydrogen bonds. So that will be times 2. And how much is for each one? 464 kilojoules per mole. So the mole is canceling out here and you're getting a number in kilojoules. So let's do all of this, the sum of everything on the product side. Amount of energy required to break apart chemical bonds on the reactant side, amount of energy that is being released on the product side when you're forming the new chemical bonds. So I'm doing this step by step. I'm adding together everything on the reactant side and I'm getting to 656 units of kilojoules. And then let me check for the product side, 2 times 799 plus I have 3,464, 54. So and that's kilojoules. So when you're calculating the delta H for the reaction, that will be your reactant minus the product. So 2656 kilojoules minus 3454. That's going to be a negative number. $798 kilojoules. That's representing an exothermic. What that information is telling you, you need an amount of energy to break apart the chemical bonds in the reactant side. And now amount of energy is being released when forming the chemical bonds on your product side. The amount of energy that you need on the product side, it's smaller. So that difference will give you a negative number. You have less energy on the product side in those chemical bonds than the one that you have on the reactant side. Final minus initial, a negative number, means that this reaction is actually releasing energy when the chemical bonds for the products are being formed. You have a net amount of energy that is not being used in the actual reaction, and we get that amount of energy, 798 kilojoules.